Right, inside that folder that I'm giving you, there are base plate in a web, and then there's 3 assemblies. Okay. Now I'm going to talk you through the analysis on the assembly with no webs, and then you're going to use the same. You're going to do that, and you're also going to analyze the assembly when it's had a web added on the bottom and a web added top and bottom, which you'll see what I mean in a minute. Okay. So the first thing you need to do once you've got the files is open up assembly no webs. Rotate the model around. You hold down the wheel on the mouse and you're able to rotate and look at all parts of the assembly. The assembly consists of this base, that plate with a boss on it. What we're going to be doing is looking at applying a load to that top face and assessing how that affects the bracket, and considering the most important thing we're going to consider is factor of safety. So we're going to apply 15,000 newtons onto that top face and look at how that would affect this bracket. And then you've got another version where I've added a web underneath here in the middle, and a third version where I've left the web in the bottom and put another web on the top. And your job is to look at the difference between the results for each of those. You'll see what I mean in a minute when we actually go through. Okay. As far as getting the files and getting that file up on your computer, and then we'll move on. Again, if you just bear with me for a minute, please. Ready, Lewis? Jack? Right. If you've wound around and got your view all over the place, quickest way back to standard orientation is to click that there and select isometric view, and that will go back to base position. Okay. Now, this is the extra ribbon tab you got now. Guys, can you just, please, we'll sort out in a minute, alright? This is the extra tab that you've got, simulation tab. Okay? Now, we're going to do what's called a study. I recommend that you don't use the study advisor. Again, that keeps popping up asking you questions about what you want to do. It's easier to just start a new study. Okay? So, we start a new study. We're going to do a static study, which is the default. So, that's what we select, and we press the tick. All we get now then is a study tree down here with various sections that we're going to need to work on. Alright, so just do the first thing and then you can work through to that, and then we'll do the next bit. First thing we need to do is put a fixture somewhere on this thing, some kind of fixture constraint. So what we're going to do is completely fix that back plate, so in the simulation that back plate doesn't move, as though I screwed to the wall, welded to another piece of metal, piece of structure or something. So what we need to do is say right click fixtures and say we want some fixed geometry. And then this blue box here is highlighted. We need to select the face that we want to fix. So that's the back face there. You can see if you zoom in, there's 3 arrows on there. What that's saying is we're fixing that in all 3 planes. We're fixing it in X, Y and Z planes. So it cannot move at all. There is the possibility, if you want to in the software, to have more complex fixtures where you only fix 1 or 2 planes. Okay, but we want to fix the whole thing in all directions. Once you've done that, you tick and you've got your fixture, and that's listed there as fixed 1. So if you do that bit, and then we'll move on to the next bit. So to put the load on, we go to external loads, right click. Can we do it afterwards, please? Yeah? So looking this way would be good. Force. The first thing we need to do is say where we're going to put the force. So we select that top face. Okay. The arrows indicate the direction of the force. So if you wanted a pull up from that boss, you could click that and the arrows go upwards. Okay. We want the force to be down, and we want 15,000 newtons of force, and tick. We've now got a force 1, 15,000 newtons in our list of forces. So if you could just do that one, please. And last thing that we have to do before we run the break that object up in a triangular pyramids of sections that then does the maths on each of those to calculate the overall effect. Okay, so what we need to do is right click mesh and say create mesh. You can change the density of the mesh, but we're not going to do that. We're going to leave that at the default. Okay, if you have a coarse mesh, it reduces the accuracy of the results. If you have a really fine mesh on a complicated object, it could cause the computation time to be much longer. Alright? When you get more advanced with this, and you know you've got areas of specific concern, maybe like in here there's a fillet or something, you can actually set finer mesh in areas where it's needed and leave it coarse in other areas where it don't matter so much. Okay? But we're not going to go into that kind of detail. What we do is leave the standard centered mesh factor, and we're going to tick. And you get a dialog box for a short time. And then the mesh is set up like so. Move on to the analysis. So we can do now, have a meshed, we're ready to run the analysis. So all we do is simply on run. Doesn't take very long, this one. He says. Nope. Well, I didn't think I'd normally take that. Always good. And it's going to talk you through that you've already got. First, we've got a stress analysis. Okay? It says what the stress is in newtons per metre squared. The red areas, the blue areas are 3,000.2 newtons per metre squared. The red area is 340,614,400 newtons per metre squared stress. Okay, so the colours give you the range of stress from the lowest to the highest. Alright? You're going to do that for each of the bracket styles. And the importance there is that you compare the stress for three brackets. So in your report, you don't want everything about one bracket and then everything about the next one and everything about the last one. You want to compare like analysis with like analysis for each bracket. Do you understand that? Yeah? The next analysis we've got is displacement. This tells you how far that bracket's been bent. Now, guys, listen, visually, what the software does is exaggerate that bend so you can see visually the direction of it. Here, the red areas have moved 2.346 millimeters. Yeah. Blue areas have moved 1 millimeter times 10 to the power of minus 30. In other words, not at all. Okay? So that is movement of each area of the bracket in millimeters. The last one is the strain. As you should know, probably better than me, that strain is a ratio, doesn't have any units, but we range from a strain of 1.163 times 10 to the minus 3 to 2.335 times 10 to the minus 8. You need to be comparing those figures for each bracket style to see, because you could find, yes, there's less stress over less area or strain over less area in the revised brackets, but the overall strain value could be increased in certain points. So that's what you need to be looking at. Alright? Now, as well as those three, we're also going to look at factor of safety. Ready, Don? Alright, I'm going to show you how to set up the factor of safety analysis. Two different ones, okay? And then you're off, then you can do your analysis, and I'll help where needed. Alright? So, first of all, you need to right-click results and say define a factor of safety plot. Okay? Now, if we look over here, this particular dialog box is one where you've actually got 3 pages to it, 3 sections. You've got a little arrow up here that allows you to go backwards and forwards. We don't need to do anything on the first page. We don't need to do anything on the second page. The third page is where we can choose between the factor of safety distribution or finding areas that are below a certain factor of safety. We're going to do both of those. So first of all, we do the factor of safety distribution, so I just tick. That shows that the red areas are factor of safety of 0.65. Blue areas, if there are any, would be a factor of safety of 73,000, and then all the other colours are somewhere in between. Okay, so that's factor of safety with that load. If you're gonna make this bracket, Seppi, and you're gonna load it with 15,000 newtons, you're not going to make it so it will only just take a load of 15,000 newtons. You're going to include a factor of safety, which is usually a multiple. So we're going to look at a factor of safety of 5. So what we're saying is we want to make this bracket so it will take 5 times 15,000 newtons without breaking. So if it gets overloaded, it's not going to break. That's the idea of a factor of safety. Yeah? So the second one that we want to look at is we right-click results again, do a second factor of safety plot. This time, in the last section of the dialog box, we tick that, areas below a factor of safety, and we put in 5 in there, and tick. What that does is it only uses 2 colours. Blue lies within, is good for a factor of safety of 5, but the red areas would fail on factor of safety of 5. Yep. So they would not comply with that factor of safety. Now, in your assignment, you're asked to look and do those 5 analyses for each of the 3 brackets, determine whether any of them will comply with this factor of safety of 5. And if they don't, you're asked to find out what load they would take to a factor of safety of 5. I'm not expecting you to do hundreds and hundreds of analyses, but you'll choose distances apart to try and find where that bracket is completely blue and there are new areas that fail factor of safety of 5. What load could you apply to this bracket? You might choose this one with new webs. You might choose, the idea is from the initial analysis you'll decide which is the best design, and then you'll assess what that design could take as a load. Okay? Yeah. Not that I know of. No. You're looking at setting up or changing the load and running the analysis again. So, I mean, the way I'd probably go about doing that is the old half-it rule. So you go down to 7,500. If that's all okay, then you go halfway between the two, and you're kind of halving the problem all the time. But I'm not looking for you to go down to the nearest Newton. Okay? The nearest, I would suggest the nearest 500 newtons is plenty of a load that would be acceptable. Whichever one's the nearest 500 newtons from 15,000 that will fit with a factor of safety of 5. Okay? Everybody clear? Yeah, well, you got in, yeah? Yeah.